Hi, everyone. I'm Dan Anderson from Intel. I'll be giving a talk on Hyperledger Sawtooth, a technical overview. The slides here are from Dan Middleton. The agenda will be first talk about blockchain basics, then design motivations for Sawtooth, Sawtooth architecture, and Sawtooth application development. Okay, a blockchain is a distributed ledger. It started with Bitcoin, which is a cryptocurrency, but Sawtooth blockchain is more of an enterprise blockchain or distributed ledger. It has no cryptocurrency. It does have state. So your state is your global state that you store your objects, your data, and the blocks, the transactions in a block are modifications or transitions to that state. The difference between a blockchain and distributed ledger, they're mostly the same, but blockchain is just a particular way you implement a distributed ledger. So many people prefer the term distributed ledger because it's more encompassing and more general. But they're both a peer-to-peer network, and you're supposed to replicate the data among all the nodes of the blockchain network. So why do you use blockchain? Blockchain is for mutually distrusting organizations, what I call frenemies, that need to update the same set of data. The key is for blockchain, the key concept is it enforces trust among this group of frenemies. There's no third-party organization that you have to rely on. It's just distributed among all the members of that group. You could do that because the blockchain is immutable. No transaction can be deleted. You can't add transactions except at the very end of the blockchain, and you can't reorder them. And all the blocks are signed, and there's hashes to prevent the blockchain from being altered. It is a peer-to-peer network, so it has an advantage of high availability. It's crash fault tolerant. Depending on your algorithm that you use for consensus, it's either crash fault tolerant, CFT, or better yet, it's Byzantine fault tolerant. And that means it protects against malicious or bad actors. There's also the concept of liveness. Liveness means that all nodes will eventually agree on a value, will eventually settle on a value, as opposed to just looping infinitely. It's a finite settlement. So why do you not use blockchain? There's a few reasons. Speed. If you want a lot of speed, you're not going to get it with a blockchain. So with a centralized database, you get millions of transactions per second, or you can. With a blockchain, it's more likely in the hundreds of transactions per second. So that's several order of magnitudes of difference between the two. And even with a distributed database, you get faster transactions per second. Also, the transactions are not private. They are public, available to everyone who has access to that blockchain. It's so you can inspect the blockchain for alterations and make sure that nothing funny has gone on. And in order to do that, you have to make it available to everyone in that, at least anybody in the blockchain network. Now, private transactions is an active research area, but it's really not solved yet. When people talk about blockchain security, they don't talk about privacy of the transactions. They mostly mean that the blockchain will still be available and accessible, and also that the blockchain will not be modified. Confidentiality, privacy is something else, and that's really not there yet, although, as I said, it's a research area. There are some bad blockchain shortcuts that other blockchain architectures have made. One is a centralized architecture. That's something you may want to use in, say, with a mainframe sort of architecture or platform or setup. And that really reduces the value of a distributed ledger. You lose the reliability. There's no multiple copies out. There's no definitive multiple copies out there. Another bad blockchain choice is having no ledger state, no database out there. So what you do for privacy, a way to get privacy out of blockchain is just to commit the transaction receipts. That is probably a hash or digest of the data of the transaction, but not the transaction itself. The problem with that is that just turns the blockchain into an opaque event log. You don't have the data out there, you just have kind of signatures of the events. And so you really don't have, the blockchain doesn't have anything on it. There's no content. You kind of, it's a bad choice because you really, you get your privacy by not exposing anything. That is, you reduce your exposure by not exposing anything. You just have zero content out there. That's really not a blockchain either. So let's talk about Sawtooth design philosophy. It's designed for scale. You could have a few nodes, or you could have several nodes. The default or base consensus algorithm is POET, and that scales, and it's a very efficient algorithm. It doesn't require the electricity of a small city in order for it to operate. And allows for several nodes. Another design choice is ease of use for development and employment. We support several languages in the SDK and the API, so hopefully a language that would be good for your application choice, for your problem set, will be there. Another choice is to keep distributed ledgers distributed. You don't centralize the blockchain. Every node on the Sawtooth blockchain has the same exact copy, same definitive copy of the blockchain and global state. It's also modular. You could swap things in and out. You could change consensus algorithms. You could change consensus algorithms on the fly without restarting, without reinitializing, without recompiling. You could add and subtract transaction processors on the fly too. You could have separate, distinct sets of transaction processors on the same blockchain at the same time. There's also a sandbox for smart contents to encapsulate and keep contracts safe by just restricting them to that address space for that transaction family, for the smart contract transaction family. So now we're going to go into Sawtooth 1.0 architectures and features. Sawtooth 1.0 was released earlier this year in 2018. For transactions, we allow parallel execution and we allow multi-language support. Both of those actually aid in performance too by having parallel processing of your transactions that speeds things up, assuming that the transactions do not conflict, that is, they do not change or alter the same parts of state, the same objects. You could execute them in parallel, and Sawtooth allows that. Multi-language support allows you to choose the language best for your problem space, and also what you want. So you could choose, for example, Python if you want rapid development just for prototyping, and later on, or instead, you could use another language, for example, Go or Rust, that is compiled, and that gives you performance. So you could choose a language that best fits your solution. Sawtooth also has on-chain governance. The configuration lives on the blockchain. In other words, we use the blockchain to implement the configuration. Updates and distribution of the blockchain variables is very easy. You just make update on the blockchain and the new variables are there. You could also have configuration on a per node basis. So if you use configuration files, you could set the same configuration settings, but it would just apply to that one single block, which in some cases you may want, but it's a lot easier just to keep your configuration on the blockchain as long as it applies to every node, and that's usually the case. We have distributed applications. There's Seth. Seth runs their Ethereum smart contract on Sawtooth using the Seth or Sawtooth EVM, which is the Sawtooth Ethereum virtual machine that allows you to run Solidity smart contracts on Sawtooth. We have a supply chain application. That's one of the use cases, but not the only one for Sawtooth. And it's a good base to start with if you have a Sawtooth, or if you have a supply chain application you want to implement on Sawtooth. So that allows to track the provenance of goods, that is from supplier, creator, to the transportation, to the merchant, to the customer. So that kind of allows you to follow the entire chain of custody of goods. For one example might be, for example, tracking fish from sea to table. So let's start with the basic Sawtooth concepts here. On the left, we have clients that submits transactions. It also queries the global state, the database for values. The client could be a web browser application in JavaScript. It could be a CLI just on the command line, or it could be embedded in some server or daemon on some platform computer system. And so the clients submit transactions, then you have the validator that kind of controls access to the database and submits transactions to the appropriate transaction processor for that transaction family. And finally, the transaction processor that handles all the transactions for a particular transaction family, that is for your application. And as I said before, you can have multiple transaction processors, and they could be for the same transaction family or for multiple different transaction families. You want to have multiple transaction processors for the same family just to increase throughput and performance. And you could also support any number of transaction families on the same blockchain. So let's add a couple more pieces, dive in here a little bit. On the left, bottom left, you see other validator nodes. So This is just illustrates one node, but it's one node in a network. So I want to emphasize that you have a network of Sawtooth validators, and they all contain the same blockchain and the same global state, and it's a peer network. They're all equally powerful, and they both have the same function of processing and storing transactions. And on the right, you have transaction processors again, as for one or multiple transaction families. So let's dive in a little bit into the Sawtooth node. You have the REST API. The client submits transactions using REST API, which is a very familiar web interface. You have POST and GET, and with several different commands available. The REST API just submits the transactions from the client to the validator. And there's an interconnect bus that does all the networking using 0MQ. You have block management, and the main purpose of block management is just to produce and consume and manage blocks. And it's kind of controlled by the consensus algorithm. You have a consensus algorithm decides what node is the leader and what node gets to publish the next block. And you have a peer-to-peer network at the bottom there connecting to your peers, your peer Sawtooth nodes. And on the right, again, the transaction processors for that node. And all nodes have the same set of transaction processors. They all have to support the same set of transaction families. So what does that give us? So one is we could have Sawtooth is a little different from some other blockchain architectures. We allow multiple transactions in the same block to affect state. So you can modify the state and have the next transaction modify the same state. They don't have to be in separate blocks. We also allow parallel scheduling, which is also not available or kind of unique in Sawtooth, not available in other blockchain architectures. So if there's no conflicts in your input and output list, Sawtooth, and you have parallel scheduling enabled, Sawtooth processes both transactions at the same time. Of course, to do this, you have to have parallel scheduling enabled instead of serial scheduling. And also in your transaction, you have to list all your inputs and outputs. You could just default it and say, I don't want to list them, but in that case, you'll process transactions in serial. But if you do list the data that you modify in your input and output list, that allows Sawtooth to speed up transaction processing with parallelism. The parallelism is aided with the transaction processors. You could have multiple processes for the same transaction family out there, ready and willing and ready to run and process transactions. If the language supports it, for example, Rust or Go, you could also have multi-threaded transaction processors that process transactions at the same time. Another feature is multiple language support. So in your clients, you have multiple choices in your implementation language. You got Python, JavaScript, Go, Java, Rust. The choice of language really depends on your application. So if it's a web-based application, for example, you'll probably want to choose JavaScript. If it's something that's embedded, you probably want to compile language like Go or Java or Java's not compiled, sorry, Go or Rust. If you want some rapid prototyping, you could choose Python. And for clients, performance is not as critical as for the transaction processors. So Python and other scripting languages are perfectly acceptable. For a transaction processor, which processes transactions for your application. You have choices of Go, JavaScript, Python, C++, Java, Rust. So you want to, for instance, choose Python for rapid prototyping to get your application up and running fast. If for efficiency, you probably want to choose Rust or Go or other compiled languages. And if you want multiple threads, you don't want Python. You probably want something like the other ones, Go or Rust. So the point is you could choose among the languages that are supported. It's not just one language that you have to use. Also, the language used to implement the transaction processor does not have to be the same as the language used to implement your client. In fact, it's probably best if they're different because the language probably solves different problems. For your client, you probably want a language that's easy, that's compatible with your application, and it's probably easy to submit. So JavaScript for browsing or one of the other languages for other kind of clients, like command line clients would be best. Well, for transaction processor, you probably want something that's very efficient because you want high throughput. So you probably want a compiled language like Rust or Go if that's your goal. If you just want to get something up and running quickly, just as proof of concept or as an initial pass, you probably want Python. So again, don't feel bound to have the same language in your client as in your transaction processor. And the reason for that is that your encoding of the transactions is basically language independent. But I'll talk about that later. Seth, as I said, is the Ethereum virtual machine transaction processor for Sawtooth. It integrates Ethereum smart contracts written in Solidity, a language supported for Ethereum, and it also has a JSON RPC interface, which is often used with Ethereum. For Seth, we have added the identity transaction processor and block info transaction processor. So that allows us to implement Ethereum identity, providing some identity and key store management, and block info provides information, some metadata information about blocks. The settings transaction processor is mandatory for Sawtooth. It always has to be present. It's required because it manages the settings, on-chain settings for the Sawtooth blockchain. And the Seth transaction processor is implemented using the Burl EVM. Burl is another Hyperledger project, and Seth uses Burl to implement Ethereum virtual machine smart contracts. Okay, so the on-chain settings are, well, here's some examples here. So for example, if you want to set the poet target wait time to 5, you set sawtooth.poet.target wait time. They're dotted variables in a tree kind of structure. So, and another example is Sawtooth validator max transactions per block. In this case, it's set to 100,000. You could also set it to some more complicated, like a list of strings. Transaction families, for example, is set to a set of pairs, which is the family name and the version for that transaction family. All these settings are kept on the blockchain, and if you want to make changes, you vote on them. If there's only one node, of course, the setting always wins. But you could set the voting algorithm you use on the blockchain too. So, for example, do you just want a simple majority to win, or do you want a certain number to win? So Or maybe you want to require every node to approve to make a change in setting. So that voting algorithm is also on the blockchain. Settings are also extensible. You could add new settings at any time without reinitializing the blockchain. And you could make settings, create settings just for your application. The motivation is that a blockchain could be managed or used by different organizations that don't trust each other. So you want the settings to also be managed by a blockchain and not have anything shady under the table. But if you want, you could have off-chain settings which apply just to that one node. It won't be, that's not really recommended, but if you just want a setting that just applies to one node or a few nodes, you just use configuration files for those nodes and set them there in the configuration file. But again, that's very hard to manage because you've got to make sure the updates are distributed, and it's just easier just to use blockchain for your settings and governance. Consensus algorithms, as I said, Sawtooth supports multiple consensus algorithms. So let's get into a few concepts here. A leader is somebody who could add a block to the blockchain. A consensus is agreement among the nodes on who the leader is, that is, who could add a new block to the blockchain. So a consensus algorithm decides on the leader, and the leader creates the new block. So let's look at, let's see, well, first let's look at some consensus types. We have Byzantine fault tolerance, BFT, versus crash fault tolerance, CFT. The difference is Byzantine fault tolerance withstands bad actors, that is, malicious actors on the blockchain. Crash fault tolerance does not withstand bad actors, bad or malicious actors. It just withstands crashes, that is, faults from a machine freezing, rebooting on itself, or maybe even catching fire or something. But so it could withstand accidents, but it can't withstand malicious play. The other way to classify consensus types is classical versus Nakamoto consensus. Classical consensus algorithms decide who the leader is with an election, voting. Nakamoto-style consensus decides who wins with a lottery. For example, Bitcoin, the original blockchain algorithm, uses Nakamoto consensus proof of work. So they solve a cryptographic puzzle to decide who the winner is, which is essentially a lottery. So let's look at a few consensus algorithms. Consensus algorithms is an active research area because people are trying to find something that's more efficient and more scalable than some of the algorithms we have now. So proof of work, the original classic consensus algorithm that was used with Bitcoin and later Ethereum, it is what miners used. It solves a cryptographic puzzle. That is, how many leading zeros can you find in a hash? And the one who could create a hash with the most leading zeros wins. And in the way you do that is you just run the hash algorithm SHA-256 over and over again, and that just consumes an awful amount of energy. It's really kind of immoral the way it wastes energy. So this proof of work is classified as a BFT, Byzantine fault tolerance, which is very good, and it's a lottery, a Nakamoto style consensus. Another BFT algorithm is also a lottery or Nakamoto consensus is proof of elapsed time, POET, which is implemented in Sawtooth using the Intel SGX hardware. And this is very efficient. It doesn't consume gobs of electricity. And the way it runs is all the nodes choose a random wait time and it waits that amount of time, and the first node that expires wins. The one with the shortest wait time in the future wins. And cheating is avoided with several mechanisms. One of them is it's cryptographically, the wait time amount is cryptographically signed within an SGX enclave and cannot be altered. And there's a certificate issued, a wait cert, that certifying that that's a valid wait time. There's also checks among the various nodes to make sure that a node does not win too frequently and does not submit or try to game the system here by by submitting transactions right after creation, for example. They have to wait a little bit before they could start proposing blocks. Another consensus algorithm is CFT, is POET CFT. This is just like, well, exactly the same as POET, except it does not use SGX. It uses an SGX simulator. So that's very good for hardware that does not support SGX, and that's, for example, in a cloud environment. A lot of, or many cloud environments do not allow you to have a processor with SGX yet. The disadvantage over disadvantage of POET CFT, that is the POET with a simulator, SGX simulator, is that it's only a CFT algorithm, not a BFT. The POET with SGX is BFT, that is, it withstands bad actors, while the CFT just is crash fault tolerant. It does not withstand bad actors. But on the other hand, people are sometimes perfectly happy with CFT, especially in a enterprise blockchain. Raft, for example, is another CFT algorithm. So Raft chooses the winner by election. So there's a leader elected in Raft among the nodes, and that one gets to choose what is the next block in the blockchain, and that leader stays leader until something wrong happens. For example, it disappears from the network or hangs or something, and another leader is elected. Then another popular consensus algorithm is PBFT, practical Byzantine fault tolerance. And this is BFT, which is very good. It withstands bad actors, and the winner is decided by election. And PBFT has been used for a while in database replication, distributed databases. So it's a well-known algorithm. The unfortunate part about it is it does not scale. So you could use it, and it's actually recommended if you just have a few nodes, say under a dozen or something like that. But it's O to the n squared. That means it has it's exponential in its messaging. So the more nodes you have, the more messages you have on an exponential basis. So the messages used is n squared. So if you have 10 nodes, it creates 10 to the second, or 100 messages. If you have 100 nodes, well, that's what, 10,000 messages. So it's fine if you have a few nodes, but as you see, it quickly gets out of hand as you add nodes. Sawtooth is kind of unique in that it has dynamic consensus. So some blockchain platforms claim to have pluggable consensus, and what they really mean is that, well, you could change your algorithm, even though we only support one. You could change it, but you have to recompile your source. Or you say, yeah, you could change your algorithm, but you can only change it when you initialize the block at creation time. But Sawtooth allows you to change your algorithm dynamically after the blockchain has been committed. So, for example, you could decide on your blockchain algorithm, and if you find a better one later, a year later, you could change it then. And that's very good, because consensus algorithms is a very active area of research, and there's new proposals and new improvements coming out all the time. It's still not a settled research area, but I think with all the work on it, something better will come up. So that kind of future-proofs your blockchain by allowing you to change it. Another example is maybe you find out later after deploying your blockchain that no, this consensus algorithm really is not the best choice, and we wanted to use this instead. So this allows you to change it. Sawtooth supports multiple consensus algorithms now. POET, of course, is the famous one, proof of elapsed time, and there's POET that uses SGX, and there's POET without SGX, that is the CFT POET. There's also dev mode consensus. That's just a very simple consensus algorithm, and that's used just for development and experimental purposes, and that's appropriate if you just have a few nodes and you're playing around with it, with Sawtooth. There's also raft consensus, as I mentioned earlier in the previous page, and that's the newest one to be added. It's still being stabilized a little bit, but it's available now. Then there's PBFT. That's not available yet. The source is out there and it's being worked on, but it's really not ready for release yet. Next, we'll talk about Sawtooth application development. So, what do you have when you develop a Sawtooth application? You create a transaction family, which has three parts: a client on the left, which creates transactions, and a transaction processor on the right, which verifies and consumes transactions. And you have a data model that's in the middle. The data model is how you define your transactions and how you define your data objects. So what's the advantage of doing this? That your application is now separated from the complexities of creating and managing a blockchain. You just have to worry about your application space. You don't have to worry about consensus algorithms and nodes and networking and distribution and all that. You just focus on your application. So, transaction processor can be roughly thought of as a smart contract. Transaction families encapsulate the business logic for your application on Sawtooth. And it could be a very simple thing, like you could just have a single transaction format that the processor processes, or it could be very complex. So a transaction could have opcode, and it could have several different fields, and it could even be something complex as a virtual machine that implements Ethereum, as is done with Seth. But so the choice of your transaction family complexity and format is all up to the developer. And Sawtooth also allows multiple transaction families to coexist at the same time on the same blockchain, each having a separate global state, but the same blockchain. So let's talk about the API here a little bit. The transaction processor API has 4 interfaces. There's register, that's when you register your instance of a transaction processor. And as I said before, you could have multiple transaction processors running at the same time. In that case, you have multiple register calls. And then you also have the other functions are apply and get and set. So get and set is used to get and set values in the global state that's stored in the validator. So the transaction processor has access to the objects in global state, and it could read or modify them. Finally, in the middle there, you see the apply. The apply is the how apply function or method processes the transaction. So you have an incoming transaction, the validator calls apply, and it gets in the transaction processor. And it usually validates the transaction, and through a series of get and sets, it processes the transaction. For example, for a simple bank account application, you may want to debit you get the amount in the account and get the amount you want to debit. You subtract that amount and then set the new value in that account. And you may also probably have multiple accounts. So with get and set, you process your debits and credits and everything, and finish processing that. So the main work is in your transaction processor is the apply method. The register and get and set is already there. They're in the base class. You rarely need to do anything with that. You just use what's already there in the base. So your main work is the apply method, which processes a single transaction. The client. We all love clients. The client could take several forms. It could be a CLI, command line client, and that's surprisingly common still. It could be a GUI, a graphical interface on your desktop application. It could be embedded in a server, daemon. It could also be a web-based or browser app. So you can take whatever form is best suited for your application. And what it does is it creates transactions and submit them to a validator node. Another function of the client is also simply to read values from state. So if you're just reading and want to get the value of some object, you could call, the client calls the validator and gets the object, and that does not even involve the transaction processor at all. It just accesses what the current value is in the blockchain global state. So these queries are made through the REST API, which is just a standard way of doing application development and transactions on the web. So you do, let's see, I think I have the example here. No, I don't. That's later on. So anyway, yeah, so with post and get, there's several REST API calls. I don't have a list here. I thought I did, but post is where you post a new transaction, and get is where you want to use to get values from state. So let's look into what's in a transaction. A transaction has a payload. Look at the bottom left there, you see payload. That is defined by the application. It's the format and the serialization is defined. Usually the serialization has to be something that's deterministic, so it never changes. So you want, because you don't want something to serialize one way one time, another way at others. So bad choices for serialization may be, for example, JSON, which could serialize sets differently. So when you store state, you always want it to be serialized in the same way because you want the hash to come out the same. The serialization method is also chosen by the application. So you could choose things like something, one example is CSV, comma separated values. So that's just a simple thing you use like in a spreadsheet. You have a value, comma, value, comma, value, comma for how many other values you have. Another method of serialization is CBOR. The one that we usually recommend is protobuf. Google protobufs allow you to serialize something in a deterministic, known order, known way, and you can deserialize with a transaction processor. And protobufs are supported in several languages, and that's very convenient because you could serialize it in your client in one language and deserialize it in another language in your transaction processor. So the transactions are serialized. You also have the global state. The global state is serialized too. So it could just be something, your global state object could just be simple as just an object, a string, or it could be an integer, or it could be something complex. So a set of several values. And in that case, you use a protobuf to serialize all those serial values as the object. So let's go back to transactions. In a transaction, we have the payload, as I just mentioned. You have the signature you have a checksum of the payload in your header, and you also have the signature. You have the signature of the header in your transaction. So you have three things: the header, signature of the header, and payload. And then the header is your hash of the payload. So that all is used to prevent modification of the transaction. A couple important fields in transaction header is your nonce. A nonce makes your transaction unique. It's a random number. A common bug with Sawtooth developers is to forget or not set the nonce. And what that means is if you have two transactions that are the same, they will have different hashes. They won't be unique. A nonce enforces uniqueness, makes every transaction unique, and that prevents replays. So if you don't set it, you could have two transactions after each other. Say you want to debit $5 and you want it from an account, and later on you want to debit the same amount, $5 from an account. If you don't have the nonce set, those transactions will come up to have the same signature, and that will confuse Sawtooth. In fact, it'd be error. So if you have the nonce set, each transaction, even if they look similar, they will be unique. Then another field is inputs and outputs. Inputs there is misspelled, but inputs is a list of, it's optional. It's a list of objects that you are reading for that transaction. And outputs is similar. It's the list of objects in global state that you're modifying. So this allows for, it's optional. You could just leave that blank. In that case, it just process things in serial. But if you do set them, it allows for parallel processing. And the way that is done is the validator makes sure the transactions don't conflict. The inputs and output lists do not conflict. And if they don't, it processes the transactions in parallel. That is, validates them and makes calls to the appropriate transaction processors. If those fields are left blank, it just then degrades into serial mode and just processes one transaction at a time, which is a lot slower. Transactions are wrapped into batches. A batch is an atomic unit of commit. All transactions in a batch must be executed, or none of them, all or none. So if there's error, say in the third transaction in a batch, all the transactions are not committed and not processed. So that allows you, for example, on a banking application, you may want to have in a batch a debit of $5 from one account and a credit of $5 to another account. That is double bookkeeping. So, but you just don't want one of those two transactions to process. You have to have both of them to be processed. So if you need them to be atomic, you put them in a batch. So transactions, one or more transactions in a batch, and you could just have one if you want. Then you have one or more batches in a batch list, and that's just a convenient way for the client to submit multiple batches and multiple transactions that are unrelated. So if you have transactions are unrelated, you just put them in different batches and put them in a batch list. If they are related and need to be all committed, you put them in the same batch. Transaction families. As I said, the data model is defined by the application. It's all up to you, the data model, the serialization, and the addressing scheme. The data model consists of two parts. One is the format of your transaction. It's the format of the transaction that is created by the client and processed by a transaction processor. This is opaque, unknown. The format is unknown to the validator node. It just passes the stuff through from the client to the transaction processor. Then there's the state. The state is the format of your object and in global state. It could be something real simple like a string or an integer, or more complex, a series of values. And how do you encode these values? You use some serialization methods. Common methods include CSV, CBOR, protobufs. So CSVs, as I said earlier, is just comma separated values like you see in a spreadsheet. CBOR is a language independent method of serialization. The method we recommend, though, is Google protobufs. And there's an example on the right of a protobuf definition. So this is a language independent way of defining your transaction and state. So it usually allows you to write your client in one language and transaction processor in another language. So let's look at this example. We have 3 fields in this message: a public key, which is a string, a name, and also a string, and timestamp, which is a long 64-bit integer. So it's, again, the format is defined by the application. Then another thing you define is the addressing of your objects in state. So the addresses in Sawtooth consist of a 6-character prefix, and then you have the 64-character address. So a 6-character prefix is unique for a particular address family. And the way it's calculated is you take the address, name of the address family, and take the SHA-512 checksum of that name, and you just truncate it to be the first 6 hex characters, and that is a unique prefix for that transaction family. Then you have the rest of the address, which is the 64 hex characters, and how you the addressing scheme is derived or created by the application. You decide how you address your objects. The only thing that has to be is unique. The addresses have to be unique for one object, and it has to be deterministic. That is, you always come up with the same address for the same object. And a common way of coming up with an address that's unique is you just take a SHA-512 digest of your object name, of your unique object name, and you truncate it to first 64 hex characters of that hash. And so your entire full address would be the 6-character address and 64 hex character, 6-character prefix and 64 character address to address into your state objects. I encourage you to look into some examples to get started with Sawtooth. The first thing you want to do is install Sawtooth and go through the tutorials of running some simple transaction families. They show examples. The documentation shows how to install Sawtooth and also how to run a simple transaction family called IntKey, which just sets a name and a value. So you could modify these integer values in this transaction family. Then you could start with some simple standalone examples after that. So you could download these repositories called Cookie Jar and Simple Wallet. Cookie Jar is a very simple application. It just stores the number of cookies in a cookie jar, and you have 2 operations. You could eat cookies, or well, first you got to bake them. You could bake cookies, create them, or you could eat them, which consume them. And you could also count them. Simple Wallet is a similar simple banking or wallet application. It allows you to create multiple people, multiple accounts, and you could have transactions. You could deposit and withdraw from your wallet for different accounts, and you could also transfer from one wallet to another wallet. So these are very simple examples to kind of show you how the API works. Then more complicated is a supply chain app. There's an education supply chain app out there, which is kind of a simple application, simplified application, and it's very good for education, for learning in Sawtooth. There's a GitHub repository, and there's several PDF files there they could go through. So you could self-study, you could go through the PDF files and follow along and do the exercises in there. And also goes through the design choices they made in that application. Also, there's a Sawtooth supply chain application that's meant as a starting point as for anyone who wants to develop a supply chain application. That is something that has a chain of custody, chain of control, and where you're transferring some asset from partners. For example, seafood. You may want to start with a fishing operation, fishing boat, and they catch the fish. Then you transfer the fish, and you transfer it to a market, and finally a consumer. And that just could track the entire supply chain of those objects. We also have a marketplace application for those who want more of that class of application. You can look into that. And for application developers, we have extensive documentation, and the guide that you probably want to start with is the application developers guide. And finally, we have the FAQ, which has frequently asked questions and answers for problems and many questions that come up in our bulletin board, our chat group. So check out Sawtooth, give it a try, go through the tutorials and the documentation, try out the simple transaction families and modify them or build your own. And you could also become a contributor. You could help out with documentation, especially when you see a problem or error or unclear part about documentation. You could submit a patch, a pull request to clarify that part of the documentation. You could contribute code, and you could also help with answering chat questions. So the Sawtooth core is in the repository. Usually you just install it, you don't compile it yourself. But if you're kind of curious of how it's implemented, the repository is there. It's open source, Apache 2 licensed. Now, all this stuff is Apache 2 licensed, but your application does not have to be. So you could choose to open source it, but you don't have to. The Apache 2 license allows you to keep your source closed if that's your wish. So we have a documentation link, lots of documentation there. We have a chat channel that uses Rocket Chat. So if you have questions, you can just jump on the channel there and ask your questions. We have several channels. The main one is listed there. And that's very good for quick questions. We also have a mailing list. So you can also ask questions on the mailing list if you prefer. And that's very good because the answers are threaded, and it's very easy. It's easier to search. So you could either choose to ask your questions on chat or on mailing list. Sorry, the light went out here. Finally, we have the FAQ link there for frequently asked questions that you may want to ask. So you may want to check the FAQ first, and if you don't find it there, you just ask your questions on your chat or mailing list. So that's it. Thank you for listening.